Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 10 on graphs of cubic polynomial functions. Alright, so earlier in this unit we explored extensively graphs of quadratic polynomial functions. Quadratics are one where the highest power is equal to 2. But now we're going to go one notch higher up to the highest power being 3. All right, now we're just going to start to explore these in this course, although you are required to know a little bit about them, typically on state assessments. In Algebra 2, you'll be looking at things with x to the third, x to the fourth, etc. So let's talk about cubic functions. We've now seen how quadratic functions have one turning point and symmetry. When we raise the degree of an equation to 3, more interesting behavior occurs. These polynomials are known as cubic functions or just cubics, all right, which is kind of a cool name. So let's take a look at a cubic polynomial, exercise number 1. Consider the polynomial y equals x plus 5 times x minus 2 times x minus 6. Letter A. Using the zero product law, algebraically solve for the zeros of this function. All right, well this should be pretty easy, especially given the fact that this polynomial is already written in factored form. So take a moment, set that thing equal to 0 and solve for the 3 zeros of this function. All right, well I like it. I don't have to do any factoring whatsoever. I've got x plus 5 times x minus 2 times x minus 6 is equal to 0. When I have the product of two or more things equal to 0, I can set each of those equal to 0. So x plus 5 is equal to 0. X minus 2 is equal to 0, x minus 6 is equal to 0, subtract 5, and I'll get x equals negative 5 is 1 0 of this polynomial. Add 2, and I'll get x equals 2, and add 6, and I'll get x is equal to 6. All right. Now letter B, right, we've talked about this extensively since our first unit on functions. What graphical features do the values in A represent for the function? All right, so like what does this even tell me about the function, right? Answer that in letter B. Well, these are the x-intercepts, right? Because they're really the coordinate points negative 5, 0, 2, 0, and 6, 0. These are all the x-intercepts. In fact, right, let's actually plot those right now, right? We're going to have an x-intercept at negative 5, we're going to have an x-intercept at 2, and we're going to have an x-intercept at 6, which is interesting, right? Can you imagine what this curve looks like such that it crosses the x-axis here, here, and here? Well, we'll see that in just a moment. But first, we have to do some beastly algebra. Let's take a look at letter C. Find the equation of the polynomial in standard form by finding the product of its 3 binomials. All right, well, we did this a little bit in the last unit when we found the product of 3 binomials. And to do that, right, we're going to have to find the product of 2 of the binomials, which will be a trinomial. And then we're going to have to find its product with the remaining binomial. I'd like you to pause the video now. Now this is kind of a lengthy process and it might take you up to like 3 or 4 minutes to do. So pause the video now, take some time and see if you can multiply these things all the way out. Again, start by multiplying 2 binomials out using FOIL or double distribution or whatnot, right? And then once you have that, typically you then have to use double distribution to multiply by the last binomial, or whichever one is the last. Pause the video now and take a few minutes to see if you can do that. All right, well I'm going to go with a couple different techniques, but the first thing that I'm going to do is I'm going to rewrite that x plus 5 down, and then I'm going to multiply these two out by using my FOIL algorithm. So I've got my first, my outer, my inner, and my last, right? I'm going to do a little combination of like terms inside. That's going to be x squared minus 8x plus 12. So just like multiplying normal numbers together, the first thing I have to do when I multiply 3 polynomials together is I have to multiply 2 of them together, right? Giving me this, and then I have to multiply by the third one. Now there is no slick FOIL or anything like this, but I could use an area method for this, I could also use double distribution for it. Actually, let me go with an area method. I kind of like that. I'm gonna draw myself a little box. All right, divide it up. I'm gonna put my x plus 5 here. I'm gonna put my x squared minus 8x plus 12 here. So x times x squared is x cubed, x times negative 8x is negative 8x squared, x times 12 is 12x. 5 times x squared is, well, 5 times x squared. 5 times negative 8x is negative 40x. And 5 times 12 is 60. I can now combine like terms. Nothing combines with my x cubed. I have negative 8x squared. Positive 5x squared is negative 3x squared. I have negative 40x, and positive 12x is going to be negative 28x, I think. Yep. And plus 60. So there's my cubic polynomial in standard form. Cubic polynomial in standard form. And now let's take a look at letter D, where we're going to allow our technology to do some magic. Let's take a look. Use your calculator and the graphing window indicated. Sketch a graph of the function as written in C on the axes given. Mark your answers from A clearly. Well, we already marked our answers from A clearly, but let's put this into our graphing calculator. I'm going to bail out of this for a second. All right, bring up my graphing calculator. Let's see. I think I can put it in. I'm missing that x cubed on the screen right now, but that's okay. X to the third, then get out of that, minus 3x squared, minus 28x plus 60, enter. All right, woo! Now I need to get the same window that I had before, so I need to move up to see what that window was. Bring my calculator back out. My window looks like negative 10 to 10 along my x-axis. I'm going to hit Menu, go into Window, Window Settings. Negative 10 to 10 along the x-axis is still okay. But then I might need something way bigger along the y-axis. I'm going to have negative 50 to 150. I think I'm even going to set my scale at 25. Why not? Since that's what the scale is. And enter. Okay. Whoops. There it is. That did not go down far enough. That's weird.
Plus 60.
Oh, it's plus 60, not plus 6. Thank you, Joey. I'm like, I got the decimal. Oh, that's even worse. Okay, let's keep trying here. 28x plus 60. I hit a decimal point before. Ha, there we go. Nice. I didn't even have my zeros in the right place, but look at this. Look at how much cooler this is than a parabola, right? This thing's got 2 turning points, goes up, comes down, goes back up. Take a look at those zeros, right? I have a 0 at negative 1, negative 2, negative 3, negative 4, negative 5. There's my negative 5. Here's my 0 at 2. Here's my 0 at 6, all right? And all I want to do is produce a general sketch of this thing. Again, I don't need to have it great, all right? But I want that general sketch. Let me put this thing on handheld only so that we can keep it up on our screen and go back into here. And let's just try to reproduce that kind of the best that we can. All right, so it kind of comes up, it peaks, it goes down, slices through that, and then goes back up. Should have arrows at the end of both of them, and that's it. Cubics have way more interesting behavior than quadratics. It's way more complicated because you've got an x cubed playing around, an x squared, an x to the first, and a constant, all of which are affecting the behavior of the cubic. All right? So, kind of cool. All right, let's keep playing around with this. Let's see some more about cubics. Now, often cubic polynomials will have 3 zeros, okay? The number of zeros, the maximum number of zeros, always corresponds to the power of the polynomial. So if we went up 1 additional power, up to an x to the 4th, we could have up to 4 zeros. X to the 5th, up to 5 zeros, etc. Now, when the cubic is written in factored form, as it was in our last problem, the zeros should be easy to identify. Let's take a look at exercise number 2. Given the function g of x equals 5 times x minus 3 times x plus 8 times x minus 1, letter A, what are the zeros of this cubic polynomial? Use the table on your calculator to verify. All right, so we'll do that in a moment, but what I'd like you to do is go ahead and use the zero product law to figure out what the zeros of this cubic polynomial are. pause the video now and go ahead and set up the algebra. Then we'll bring back the calculator to verify our algebra using tables, and then we'll talk a little bit about letter B. All right, so I've got the following equation. 5 times x minus 3 times x plus 8 times x minus 1 is equal to 0. So I'm going to set x minus 3 equal to 0, x plus 8 equal to 0, x minus 1 equal to 0, add 3. I'll get x equals 3, subtract 8. I'll get x equals negative 8, and add 1, and I'll get x equals 1. We'll discuss that 5 in letter B, so we'll do that in just a moment. But these are my 3 zeros. Let's verify it on the calculator. I'm going to bail out of this again. Hopefully bring my calculator up, put it back on this. All right, here we go. Okay, I want to go into here. Let's clear this thing out. Let's put in our new function, 5 times parentheses x minus 3 times x plus 8 times x minus 1. Let me make sure that looks good. 5 times x minus 3 times x plus 8 times x minus 1. Now remember, I don't really care about the graph so much here. I just want to verify this using my, my table, split screen table. Okay. My smallest 0 was x equals negative 8. Let me just verify that. If I go to x equals negative 8, what I see is I see a 0 in the table, right? X equals negative 8 gives me a 0. My other 2 zeros were x equals 1 and x equals 3. Let's verify those real quickly. I'll just keep this on the big view. Whoops. Come on. All right, there's my x equals 3, 0. Again, this is a very good way to verify your algebra, right? When x equals 3 went into the expression, 0 came out. And my final 0 is not there. Where is it? Oh, what is my last 0? My last 0 was x equals 1. There it is. I zoomed right on past it. There it is. My final 0, x equals 1. So much easier when I'm just holding the calculator in my hand. All right. Now, let's briefly talk about, yet again, why the 5 doesn't matter. So that's in letter B. Explain why the leading factor of 5 does not affect the zeros of this function. All right, well, it's this simple, right? If I've got the product of multiple things equal to 0, then one of them has to be equal to 0. But the 5 just can't be equal to 0, right? You know, 5 times 0 is still 0. So 5 cannot be equal to 0. And when it is multiplied by 0, the product, whoops, get rid of that, and maybe give myself a little more room. The product still equals 0, right? Again, it's really arithmetic if you think about it, right? So for instance, if I took 3 and I substituted it into this expression, I'd get 5 times 3 minus 3, that's equal to 0. 5 times 0 times, I don't care, right? 5 times 0, boom, it's over, right? Likewise, if I took 1 and I threw it in here, I'd have 5 times, I don't care, times 0. That would be 0, right? It's still a 0. If I took negative 8 and I substituted it into here, it would be 0. That would be something, I don't care what they are. I'd have 5 times a number times 0 times a number. As soon as one of those numbers is 0, the whole product is equal to 0. And the 5 just doesn't matter, right? We don't get a 0 of -5. We don't take each one of these values of x and multiply it by 5. None of that happens, right? We're just trying to find values of x that when I substitute them into this giant product makes one of these three things equal to 0. That 5 never can be equal to 0, even though it's part of the product. Okay, now as with quadratic functions, sometimes we may need to factor a cubic a bit more in order to algebraically determine its zeros. So let's take a look at a few examples like that. Exercise number 3. Consider the polynomial y equals x minus 2 times x squared minus 36. Letter A, write the polynomial function in completely factored form. All right, so in other words, right, here I've got a polynomial that's somewhat factored because it's written as a product of x minus 2 and x squared minus 36, but I claim that you can do a little more factoring on that. Pause the video now and see what you can do. All right, well, there's not much, okay? And the last thing that you would want to do is multiply this out. That's not what it's saying, right? Completely factored form means you want to factor until you can't factor anymore. And that x minus 2, well, that one's done. But the x squared minus 36, that's the difference of perfect squares. And I can write that as x minus 6 times x plus 6. At this point, I can't factor the x minus 2, the x minus 6, or the x plus 6. They're as done as they can be. Now let's take a look at letter B. Based on A, what are the zeros of the function? All right, this should be very easy given our first two exercises. Why don't you go ahead and figure out the zeros of this function? All right, it's probably at that point where, you can basically do it by just looking, but let's make sure that we go through the logic, right? I'm setting my function equal to 0. I'm setting each of my factors equal to 0. And I'm solving each one. This one would give me x equals 2. This one would give me x equals 6. And this one would give me x equals -6. So those are my three zeros. In other words, they're my three x-intercepts. Now let's take a look at letter C. Sketch a graph of the function on the axes above. Create a graphing window that is large enough to show all turning points of the function. Label your window. Make sure to accurately plot your zeros. Well, all right, before we even throw this thing into our calculator, let's do the last part where it says make sure to accurately plot your zeros, because we've got our zeros, so they're easy to plot, right? X equals 2 is going to be right here. X equals 6 is going to be right here. And x equals -6 is going to be right here. Now what I'd like you to do is I'd like you to take your calculator, and you have a choice now. You could either put in the original one, or you could put in the completely factored one. By the way, there is no need in this case, unlike exercise 1, to multiply this all the way out and get it into its standard form. Doesn't say put it in its standard form. We don't have to. The calculator is just as happy to graph this, or the standard form. I don't want to mess around taking time to do that. All right. So I'm going to actually end up putting this one in just to kind of justify it based on the original equation. But throw that equation in and then graph it. You're going to have to play around with the y window sum because of how big the y values get on a cubic graph. So go ahead and noodle around with that. Try to find a good graphing window to show the entire cubic function. Pause the video now. All right, I'm going to make this, this zero maybe a little bit bigger so we really can see it. Again, I've got to bail out of here. I'm going to just open up a brand new file. Don't need to save that. I want my graph. My graph is x minus 2, x squared minus 36. So x minus 2 times x squared minus 36. All right, enter. Okay, so before we kind of like start to play around with our window, we can already see what the problem is here, right? We can see those zeros here, here, and here, but my graph almost looks like 3 vertical lines, okay? That's because of how steep a cubic graph tends to be. So I'm gonna have some turning point way up here and some turning point way down there, and I've got to find them by making my graph window larger. So let's just play around with that a little bit. I'm gonna hit window. I love playing around with the graphing window. window settings. My X settings don't have to change at all. But what I do have to do is I have to make that larger. How big? I don't know. Let me start by going pretty big. I'm going to go negative 100 to 100. Maybe that's too big, maybe it's too small. We'll see. All right, well, negative 100 to 100 got me that turning point down here. And you can probably see that I got a lot closer to that turning point up here, but it's probably somewhere up here. Now I could overshoot, I could go up to 200, I could go to 150, whatever. Let's go back into it. Let's go into our window settings. It's that one that I need to work on. I think I'm gonna just go 200. Probably is gonna be big enough. Look at that. That's a nice looking graph there, right? I can really see the nature of that cubic coming up, coming down, coming back up. I've got those two turning points, those three zeros, which we've already plotted, right? So all I need to do now is get a sketch of this on my graph. I'm going to say that was 200. I'm going to say this is 100. I've got this nice graph that kind of looks like this. And done. I didn't quite make it go through the zeros, and this one looks a lot better than that one, but I think it'll get the job done. All right. Oh, me and my graphing on vertical boards, not easy. All right, let's take a look at another one. Exercise number 4. Given the cubic function y equals negative 2x cubed plus 6x squared plus 80x, do the following. Find the zeros of this function by factoring. All right. Well, here, we've got one that hasn't been factored at all, right? So let's start together by throwing down negative 2x cubed plus 6x squared, let's try that again, plus 80 times x equals 0. Okay. Now, normally you don't have to factor a cubic right from the get-go, like there's no factoring that's been done already, but this one we have to. And we can, right? We can because we just need to factor it completely, okay? Our first step is going to be factoring out a GCF. Now, if I look at the negative 2, the positive 6, and the positive 80, note that 2 goes into all of them. Also note that I've got an x squared, and an x cubed. Now, I could certainly pull out a GCF of 2x, but I would suggest that if the leading coefficient is negative, as it is in this case, that we should factor a GCF of negative 2x out. And let's do that together. I don't know that we've done that more than maybe once or twice so far, so I want to kind of really try to walk you through it here. So let's factor out a negative 2x and think about what's got to be inside of the parentheses. Now, again, whenever you factor a GCF out, you're really reversing the distributive property. So you just have to think to yourself, what would I multiply negative 2x by to get negative 2x cubed? That would have to just simply be positive, right, x squared, right? Negative 2x times positive x squared would be negative 2x cubed. Then I think, well, what would I multiply negative 2 by to get positive 6? Well, that would be negative 3. And then to get x squared, I'd have to have another x there, right? So negative 2x times negative 3x would be positive 6x squared. Finally, I think to myself, well, what would I multiply negative 2 by to get positive 80, right? And that would have to be negative 40. I don't need another x in there. Because the x is already here. Now, I'd like you to pause the video and continue to factor that trinomial. Don't lose the negative 2x, otherwise you'll lose one of the zeros, all right? But continue to factor that. Once you have that factored, take each one of your 3 factors, set them equal to 0, and solve. Pause the video now. All right, well, this is a pretty easy trinomial to factor. I'm looking for 2 numbers whose product is negative 40 and whose sum is negative 3. All right, those 2 numbers happen to be negative 8 and positive 5. So this is all going to factor as negative 2x times x minus 8 times x plus 5 is equal to 0. So I can now take this and set it equal to 0, this and set it equal to 0, and this and set it equal to 0. Now again, please be careful. It is very easy for students to look at this and go, oh, negative 2x equals 0, x equals positive 2. No, definitely not, right? I'm just going to divide both sides by negative 2 here. 0 divided by negative 2 is going to be 0. In fact, anytime, a word of advice, anytime you factor a GCF out that involves an x like this, well, so it's 5x, it's negative 2x, it's 10x, I don't care. X equals 0, right there, snuck in there, is going to be one of the zeros. Now here, we definitely have x equals 8, and here we definitely have x equals negative 5. So I'm going to write those down to save myself some room. Sorry, I should have given you a little more space on that one, or maybe given myself a little more space. Who knows? All right, so I've got these three zeros, x equals negative 5, x equals 0, and x equals 8. This time I haven't given you anything at all in terms of sketching. So let's take a look at letter B. Using your graphing calculator, sketch a graph of the cubic in the space to the right. Make sure that the graphing window shows the two turning points as well as the zeros. Now this is kind of cool because I want you to play around with this, and again, I'd like you to just put the original one into your calculator, set your viewing window so that you can definitely make sure you see the negative 5, the 0, and the 8, okay? And you can overshoot, right? You can have more than just that, but make sure you show at least that, and then you'll probably have to play around with that y window some, all right? So see if you can produce a nice sketch of this cubic function right over there, right, by hand. I mean, obviously, use your graphing calculator. All right, so let's take a look. Bring this thing back out, bail a little bit. I think I'll just go back to this, just do a new doc, easier, I think, graph. Okay, here we go. So we have negative 2x to the third, right, plus 6x squared, right, and then plus 80x. Excellent. All right. Again, we get something that essentially looks like vertical lines because we need to make the y window much larger. We can see our three zeros there, including x equals 0 right there, right, which goes through the origin, but I need to make this thing bigger. So let's play around with the window a little bit. Menu, window settings. I like my negative 10 to 10. I don't think there's anything wrong with that. That didn't work. You'd think that just hitting clear would have worked out on that, but no, not enough. All right, I'm gonna stick with what I started with last time, negative 100 to 100. Why not? Good guess, feels right. All right, and it got us quite a bit of the way there, right? We can definitely see that we're coming down here. There's probably a turning point right around down here. I'd probably negative 150 will get the job done there. Now here, it definitely looks like I'm gonna have to go significantly higher. So let me go into my menu, window settings. Now I'm kind of hesitant here. I might as well just go negative 200, I think. Just overshoot a bit. Oh, I still didn't get the one on the top, right? And sometimes that's what you have to do. Sometimes you have to play and play and play around a little bit more. I did pick up the turning point down here, which was good, but I need to go a little bit higher up here. Maybe I'll have to go up to 300. All right, wow. This is one big cubic. Cubics can get very large very fast. And I still didn't quite get it. That is funny. I mean, it's like up there. Close. We'll go with 350. That'll do it. There we go. Now we have everything. And again, it's that classic cubic shape. Two turning points, right, along with 1, 2, 3 zeros, all right? My window went from negative 200 up to 350, from negative 10 over to 10, right? So now I can sketch this thing. All right, first thing I'm gonna do is I'm gonna just put some basic axes down. All right, up here, I'm way up here at 350. Here, I'm at negative 200. Here, I'm at negative 10, positive 10. I want to make sure I nail the fact that it goes through the origin. right? And then I'll mark my other two zeros. Those were at -5 and +8. And I think we have it. All right, nice little graph there. I love graphs of cubics. They're so much more interesting than graphs of quadratics, which, they all basically look the same. All right, let's do one more that should be pretty easy. Exercise number 5. What are the zeros of the polynomial y equals -3x times x minus 9 times x plus 4? Justify your answers algebraically and verify using a table on your calculator. All right, why don't you go ahead and do this? It should be pretty easy, and then we'll take a look. All right, well, I just wanted to throw one last one at you. We've done actually a number of ones that look kind of like this. In fact, our last one, really, after we factored, looked very, very similar to this, right? We have -3x times x minus 9 times x plus 4 equals 0. That means we'll have -3x is equal to 0, x minus 9 is equal to 0, and x plus 4 is equal to 0. Again, this one you have to want to be very careful about. Divide both sides by -3. 0 divided by -3 is 0. Here, add 9 to both sides. We'll get x equals 9. And here we'll subtract 4 from both sides. And we'll get x equals -4. All right. I think we'll skip actually verifying this with the tables on the calculator for right now. We did that repeatedly in this lesson and in other lessons, so you should have a firm feeling for how to do that at this point. Let's wrap this one up. So what we did today was we literally took our polynomials up 1 degree, right? We went from looking at polynomials whose largest power was equal to 2, which we call quadratic polynomials, which have graphs called parabolas, up to polynomials that have the highest power or a degree of 3, right? Those became more complicated. They tend to have 3 zeros, they tend to have 2 turning points, and we can oftentimes find those zeros by using the zero product law and by factoring. All right, we won't see a lot of cubics in this course. All right, this will pretty much be our exposure to them. You will work a lot more with higher degree polynomials as you move forward in math, especially in Algebra 2 and in pre-calculus and calculus courses that you might take later on in high school and in college. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.